I managed. And today we're going to have Valentin, and Valentin's going to talk about applications of solvable lattice models in algebraic geometry. Thank you.
Great. Thank you, Slava. Can you hear me?
Yes.
Okay. So first of all, thank you for the invitation to speak in this seminar. It's really great. I'm happy to give a talk because lattice models have been very influential in my research so far. So I changed the title from what's on the website, but I think that's not very important. But let me now try to explain what I'm going to talk about. So far we've seen lattice models appear in different contexts. And one context was, and this was especially emphasized in Ben's talk, is that you can use lattice models to represent certain special functions. And the idea is that you may write a special function as the partition function of a lattice model, and you may use some standard techniques in the theory of lattice models to prove certain properties, like things like maybe like Cauchy identities or branching rules for your special functions. And we've seen so far functions that appear in combinatoric. So we've seen Schur polynomials. I don't think we've seen Hall-Littlewood or McDonald polynomials, but they're there. Recently, there have been papers studying lattice models for LLT polynomials. And I want to think about these as combinatorial special functions. We've also seen several talks on different versions of Whittaker functions that appear as partition functions of lattice models. And this is the p-adic representation theory side. And one may also study special functions that are motivated by certain topics in algebraic geometry. And this is what we'll talk about today. And the focus will be on Schur polynomials, Schubert polynomials, and Grothendieck polynomials. And somewhat, so this talk, the main idea of this talk will be somewhat different to what Ben spoke about. In particular, we want to use lattice models to give, so we still want to prove some combinatorial properties of our special functions, but most of these properties will be of the type, I want to be able to write my function maybe as a sum over certain maybe interesting combinatorial objects. Some with some weights that are somewhat easy to compute. And yeah, so this is the main motivation, is to prove these combinatorial formulas for special functions. And maybe at the end, if we have time, we'll briefly speak about Littlewood-Richardson coefficients. Okay. So before we begin, let me talk a bit about geometry, and let me try to give some motivation why one would study such functions. So we may start with a very old problem in enumerative geometry, which is how many lines intersect four given lines in general position in R3. And one may solve this problem computationally, but one may also use Schubert calculus to solve this problem. And this is what I'll try to explain vaguely how to do. And to do this, I first have to introduce the Grassmannian. So the Grassmannian, it depends on k and n, which are two positive integers. And the Grassmannian is the space of k-dimensional subspaces of C to the n. One maybe may work over other fields like R to the n and so on, but usually you want to work over C to the n. This is a smooth algebraic variety, and one may partition the Grassmannian into Schubert cells, C lambda. Here, lambda is a partition that fits inside a k times n minus k rectangle. And I'm not being very explicit here, but you may think about these Schubert cells as the set of k times n matrices who have reduced row echelon form given by the strict partition lambda plus rho. So basically the ones in reduced row echelon form will be in columns given by lambda plus rho. And for each Schubert cell, one may define the Schubert variety as being the closure of that cell. And this is in by closure, I mean the Zariski topology. Okay, so if Lex lambda denotes my Schubert variety, then this will induce Schubert classes in the cohomology ring of the Grassmannian. And one may show that this cohomology ring is isomorphic to a quotient of the space of symmetric polynomials in such a way that these Schubert varieties X lambda will be mapped to the Schur polynomials S lambda, which depend on lambda. And what is interesting here is that now multiplication in the cohomology ring will correspond to intersecting Schubert varieties with respect to generically chosen bases. So if we go back to the initial question, which was how many lines intersect 4 given lines in general position in R3, one may think about each of the 4 given lines and consider for each of them the space that intersects L. For each line L, consider the space that intersects L. And then for each space, one may associate a Schubert variety, which will also induce a Schur polynomial. And the Schur polynomial corresponding to that Schubert variety will be S1. And then where lambda is just the partition 1. So then the answer to our question is given by the following computation. So we can multiply S1 4 times because we have 4 given lines. And when you raise S1 to the power 4, because the Schur polynomials are a basis for the space of symmetric functions, you may write this down in terms of, you may write this 4th power in terms of other Schur polynomials. And this is how the decomposition works. And it turns out that it is this coefficient 2 that gives you the number of lines that intersect those 4 lines in general position. And I know I'm being very vague here, and this is on purpose. So what I want to do here is just give you enough motivation or give you enough information to pick your interest so that if you want to learn more, you can go and read more about this topic. And I think a good starting point for this topic is Sarah Billy's iSerm slides, which might already be on the website. So I did send them to Slava, and I think they're pretty great. They talk about Schubert calculus, and there's a lot of interesting stuff in there. Okay. So if you have, obviously, if you have any questions, feel free to interrupt me. Okay. So now let's assume that we have the motivation to study such special, so something like this will give us the motivation to study special functions and also their Littlewood-Richardson coefficients combinatorially. And one way to study such objects combinatorially is via lattice models. And this will be the focus of this talk. So before we go on to lattice models, let me try to give you a list of functions that might be of interest to people studying geometry. So one may consider the Grassmannian, as we've seen before. And as I mentioned, Schur polynomials will correspond. So these Schubert varieties will induce in the cohomology ring certain symmetric functions, which are the Schur polynomials. One may consider instead of the cohomology ring, the connected K-theory ring of the Grassmannian. And in this case, once one obtains what's called beta Grothendieck polynomials. These are the Grassmannian type, which will depend naturally on a partition lambda. There are also other types of Grothendieck polynomials, which we'll get to. And there are lattice models for these types of polynomials. And the first lattice model was given by Motegi and Sakai. And then Wheeler and Zinjustin gave a lattice model for the double version. The double version means instead of one set of indeterminates xi, your polynomial will depend on xi, but also on a second alphabet yi. We'll make this more precise as we move on. The difference between the two models is not so big. So in fact, Wheeler and Zinjustin's model is almost a copy of Motegi and Sakai. But what Wheeler and Zinjustin do, which is very interesting, is they give some integrable interpretation of the Littlewood-Richardson coefficients for these polynomials. Okay, so these are some polynomials. Now, other polynomials one might be interested in is, so we can consider the flag variety. The flag variety is the set of complete flags. So this means you have a set of vector spaces, V1, subset of V2, subset of V3, and so on and so forth, in such a way that V0 is just the trivial subspace, Vn is the full subspace Cn, and the dimension of each Vi is I. And the set of all these complete flags will form the flag variety or the full flag variety. One may write the flag variety as the quotient of GLN by the Borel, where the B is the Borel. And due to Bruja decomposition, we may write GLN as a union, a disjoint union of B double cosets. And this will then induce on the flag variety. So because of this, one may construct Schubert cells CW on the flag variety for W any element of Sn. And as before, we can define the Schubert variety to be the closure of a Schubert cell. So this is XW. And we actually understand how to write XW in terms of these Schubert cells. So in particular, XW will be the disjoint union of all Schubert cells corresponding to Y for all elements Y of the symmetry group that are less than or equal to W. And then you can also write it as the union of Schubert varieties, but now the union will not be disjoint. Okay, so now just as a remark, both the Grassmannian and the flag variety are special cases of a more general object, which is called the D-step flag variety. So this is just, you again take flags, but now they're not necessarily complete. So they're like sets of vector spaces V1 up to Vd, and then Vi has to be a subset of Vi plus 1. Everything has to be inside C to the n. And the dimension of Di will be Ni, which determines the D-step flag variety. And to get back the objects we mentioned before, so to get back the Grassmannian, one has to take D equals 1 and N1 equals K. And to get back the full flag variety, one has to take D equals N and Ni equal to I. Okay, so now these Schubert varieties will also induce certain classes in the cohomology of the flag variety. And these classes, as before, will be represented by certain polynomials. So if we look at the cohomology ring of the flag variety, XW will be represented by something that's called a Schubert polynomial SW. This is due to the work of many people, including Bernstein, Gelfand, De Mazur, and Lascaux and Schützenberger. And then in some more complicated setting, one may consider the T-equivalent connective K-theory of the flag variety. And in here, these Schubert varieties will be represented by what's called double beta Grothendieck polynomials. So these polynomials depend on an element W in the symmetry group. And they're also double, meaning they'll depend on two alphabets, X and Y. But these polynomials are pretty general in the sense that they recover both the Schubert polynomial by setting beta to 0 and forgetting about the second alphabet. And they also recover the previously defined Grothendieck polynomials, the ones which I named the Grassmannian Grothendieck polynomial. So those polynomials depended on a partition lambda. So to recover such polynomials, first of all, you set y to be 0, and then you focus on W to be a Grassmannian permutation. So this means that W will have only a unique descent, or there'll be a single I such that W of I is larger than I plus 1. And for such W, one may associate a partition in a somewhat canonical way. And then this is how you go from this GW beta to G lambda beta. Okay, so now the purpose of this talk is to give lattice models for these somewhat general polynomials. And also to see what, so not only to give the lattice model, but also to try to prove something with the corresponding lattice models. And there will be two, so in this talk, there will be two lattice models, but in fact, there's more than two. There's maybe 3 or even 4. I'm not sure, who knows. So I'll get to that immediately. But first, let me try to define the Grothendieck polynomial. So what I have here is a strictly combinatorial definition. And then one would have to prove that this combinatorial definition is exactly what is obtained on the geometric side. And for this, there are certain geometric techniques, like one uses pull back and push forward maps in the Bott-Samuelson resolution of singularities. And these will somehow naturally give some recursive definition of these polynomials, which will end up being exactly this combinatorial definition that I'm presenting right now. Okay, so first of all, we can define the direct sum of x and, so for x and y indeterminate, we may define the direct sum to be x plus y, x is equal to x plus y plus beta xy. SI will denote.
Sorry, can I ask a quick question, Valentin?
Yeah, go ahead.
Yeah, so I mean the usual Schubert polynomials, they stabilize, right? Do these double beta Grothendieck also stabilize in some sense? You mentioned Lascaux, Schützenberger, right? And so they write down stable growth in an infinite alphabet, just like Schur function stabilize.
Yes.
Valentin, can I answer that?
Yeah. Go ahead, Charles.
Yes, they do stabilize.
Okay.
And in the case of a Grassmannian permutation, so in the usual like stability of Grothendieck's, or sorry, stability of Schubert's gives Schur's, these will stabilize to factorial Grothendieck's, which have a similar description. And this was shown by Peter McNamara.
Okay, good. Thanks.
Okay, thanks for the question. Okay, so SI will denote some simple reflection, and W0 will be the longest word in the symmetry group. And for any polynomial f, the symmetry group acts canonically on f, so it basically swaps xi and xi plus 1. So SI will just swap xi and xi plus 1. And then we can define some divided difference operators. So first we define delta I in this form. So it will be just f minus si of f over xi minus xi plus 1. And then we can define the beta divided difference operators, which will be delta I applied to f times normalizing factor, which is just 1 plus beta xi plus 1. So with this definition in mind, one may define the Gautendick polynomial as follows. So in the base case will be w equals w0 and not w is the identity. So for w equals w0, the Gautendick polynomial will be a sum or a product over terms of this form for all I and j such that I plus j is less or equal to n. And then to obtain all the other Grothendieck polynomials, there's a recursive relation, which is given as follows. So g of w will be delta I of GWSI when LWSI is the length of W plus 1. So basically similar to how we, for example, might build Ivahori-Whittaker functions moving up in the Bruchau order, we build these Grothendieck polynomials moving down. Okay, so the purpose of this talk is to present two lattice models for these polynomials. And these were done independently at the same time. One of them by Brubaker, Frechette, Hard, Tibor, Weber. And in fact, they actually have more than one. They have at least two models. And the second one was done by myself and Travis. And these two, well, the first and the second models will be different, and I'll try to explain how they're different. Okay, but yeah, okay. So at this point, I introduced the polynomials and this combinatorial definition. So I think I'm done with geometry for the rest of the talk. So now I'll go into lattice models and applications. Are there any questions so far? Okay, so let us move forward. So the idea is we want to prove certain combinatorial properties of these polynomials. And I'll focus for the first part on the following property. The Grothendieck polynomials may be written as a weighted sum over bumpless pipe dreams. This is a recent result by Anna Weigand, and I'll try to explain what a bumpless pipe dream is and what the result is, and then so this was proved by Anna, and then I'll try to somehow explain how using lattice models gives a very easy reproof of this result. So what are bumpless pipe dreams? So these are, so you have to work with these given tiles, and you have an n times n grid, and you want to cover it only with these given tiles, such that paths continue once you move from one tile to the other. And you always have n pipes, so these will be called pipes, these paths. And you always have n pipes starting from the bottom edge and ending at the right edge. So as we can see in this example, we have 3 paths starting at the bottom edge, and then 3 ending on the right. There's nothing on the left and nothing on the top. And each 1 by 1 tile will have to be one of these 6 tiles. So this is an example of a 3 by 3 bumpless pipe dream. And for each bumpless pipe dream, we may define the key. And the key is an element of the symmetric group. And to given a bumpless pipe dream, to compute the key, one must trace the paths and record the intersection via simple reflections. And then one must use the de Mazur product. So basically, if you have the same SI appearing twice, if you square it, you don't get back the identity, but rather you get back SI. And I'll do an example which is not somewhat trivial. But if you look here, what happens is we can think about this bottom as being 1, 2, 3. So this is path 1. And path 1 at this point intersects path 2. So we're going to get a S1. Then path 2 intersects path 3. So we're going to get an S2. And then path 3 intersects path 1. So we're going to get an S1 again. So this is just W0. This is a somewhat trivial example. We'll do an example immediately. So these are bumpless pipe dreams, and these are keys.
Sorry, how do you know which intersection precedes which in what you are writing down?
You go from
Is it by diagonals or something?
Yeah. You go along diagonals from left bottom to top right.
Okay.
Okay. So now let's do an example and somehow write down all these bumpless pipe dreams. So I take n equals 1, and I take the following W, S1, S3, an element in S4, and now I want to write down all the bumpless pipe dreams with key equal to W, and these are all of them. So for example, given this bumpless pipe dream, it's somewhat pretty easy to see that the key will be S1, S3, because basically you have this intersection here, which corresponds to S1, and this intersection here, which corresponds to S2. Now, the only non-trivial case in this example will be this bumpless pipe dream. So here we have one intersection between paths 3 and 4, and this will correspond to S3. But then we have 2 intersections. We have an intersection here and an intersection here. Both of these will correspond to S1. And what we do is we use the fact that we use the de Mazur rule. So S1 squared is S1, and we get just S1, S3 instead of S1 squared, S3. Okay. So then there's a theorem by Weigand, and the theorem says that you may write this Grothendieck polynomial as a sum over bumpless pipe dreams with key W, and the sum is of some weight of P. And the weight of P is very easy to compute. So you look at P, and basically you'll have a product of these weights, beta xi plus yj, for every tile that's empty. So for example, so the I and the j are the coordinates of the tile. And then you also have another product of 1 plus beta xi plus yj for every tile that looks like this. For example, this tile. Okay, and the proof is combinatorial and somehow involved, and it's based on some work of Lascaux. And what we can do, and what I'll try to explain next, is how to reinterpret this problem in the language of lattice models and how to give a very easy proof once you have the lattice model.
Sorry, can I ask one question about the previous slide?
Yes, this one or even?
Yeah, this one. So you're writing at the top W is equal to S1, S3. So S1 is the transposition between 1 and 2, or?
Yes. Yeah, so S1 is the transposition between 1 and 2, and S3 between 3 and 4.
Okay. No, I was just a little confused because you write that SI squared is equal to SI.
Yeah. So this is not a relation in the symmetry group.
Mm.
But this is a relation that I'm using to compute the key.
Okay, only to compute
the key. I track all the intersections and all the SIs corresponding to the intersections, and then I multiply them using the de Mazur rule, which says that this relation will happen. So, for example, for this boundless pipe dream, I have two intersections between these pipes, and then so I get S1, S1, and then I have another intersection here, which will correspond to S3. And then I use this rule that S1, SI squared is SI. And this gives me key of P equal S1, S3.
Okay, thank you.
No problem. And yeah. Okay. So now let's talk about colored lattice models. So the lattice, this will be one of the lattice models, is the one that Travis and I came up with. And it will help us understand, it will help us give a very easy proof of that theorem. So our model is colored. So as usual, we work with colors C1 through Cn, and they'll be ordered. So I want C1 to be larger than C2 and so on. And 0 will correspond to no color. The lattice model will be n times n grid. That looks something like this. We've seen this before many times in the past. And so I need to explain parameters. So each row will be assigned parameter xi, so rows. And each column will be assigned parameter yi. So at each intersection, there'll be an xi and a yj parameter. The boundary conditions will be uncolored on the left and on the top, and colored on the bottom and right. The color on the bottom will be given by C in this particular order. So the highest color will be to the left, then the next color, and then the next color. And the boundary on the right will be given by C permuted according to W. And then we may assign colors or uncolors to every interior edge, and we may compute the weight of such states, and then we may compute the partition function, which is just the sum of weights over all possible assignments. So this is what I denoted by Z of, so SW beta will be this system, and Z will be the partition function of this system. And it will depend on W, and there'll be parameters X and Y, and there'll be I don't think quantum parameter is the right word, but let's say quantum beta. Okay, so this is the partition function of this lattice model. And the theorem is that the Grothendieck polynomial is exactly the partition function up to a power of beta to the length of w. Okay. So how do we prove such a statement? The proof is somewhat standard. We've seen, I think, many proofs so far, and it's somewhat the same idea. So what we do is, once we have the weights, this is important, and I'll get back to this at some point. So once you have the weights, you need to find a solution of the Young-Baxter equation. And this was done using sage computation and some guessing. Then you need to prove, you use the solution of the Young-Baxter equation to prove certain functional equations using the train argument. And then you compare these functional equations to the functional equations for the Grothendieck polynomial, which are obtained using the beta divided difference operators from before. Then you need to look at the base case. So the base case is w equals w0. This was given explicitly, and one may compute the partition function at w equals w0 relatively easily. And then once you match the base case and once you match the functional equations, then you get that the two objects will be equal. Yeah, so basically it's pretty standard. Are there any questions? Okay. So now recall the theorem of Weygand, which says that the Grothendieck polynomial is a sum over these boundless pipe dreams. How can we prove the theorem using our lattice model? The proof, in fact, is very, very straightforward. So there will be a weight preserving bijection between states in the model and boundless states in the model SW and boundless pipe dreams with key W. So here is an example of how this bijection works. So let's work with W is S1, S3. So remember, this was one of the boundless pipe dreams that we had. So,
sorry, why is this cheating, Valentin? You said it's cheating. Why is it cheating?
So once you have the model, so the cheating is, I'll try to explain maybe next slide, or I can maybe do it now. So morally, we know the weights. It was very easy for us to determine the weights, because once you understand the theorem, Weygand's theorem, and once you understand the weight of the boundless pipe dream, it's very easy to move this. It's very easy to move the boundless pipe dream to like a state of the system and figure out the weights. So basically, I'm starting to with some weights that I had inspiration for.
Okay.
And the inspiration for these weights was coming from here. So if there was no such theorem, it's unclear if I could have come up with it. If there was a conjecture and no proof, I could have come up with these weights easily, and then everything would be fine. But if there is no conjecture, so then it's sorry, does this answer your question?
Oh, absolutely, absolutely, absolutely. I mean, there's no cheating in the proof. The cheating was that you were inspired.
Yeah. So not inspired by the proof, but by the statement. So again, if we had the conjecture, I think everything would have been the same. But if we had no conjecture, I think it would have not been so easy. Possibly, I don't know. Okay, so how do you go from how do you write the bijection between the states and the boundless pipe dreams? So if I give you a state, basically we can write it in terms of colored paths. And what I do is I simply forget about the colors. And this will trivially give me a bumpless pipe dream. So moving from left to right is very easy. Now, how do I move from right to left? And this is also not hard to see. So what I do is I color the bottom. So this will be color 1. This will be color 2, and so on. So I color this first line red. And then I color this blue. And then I follow the lines. So here I have red and blue intersect. And if I look at my weights, red is larger than blue. So if I have red from the left and blue from the bottom, this is the only possible configuration that will give me an admissible state. So a state whose weight is not 0. So because this is the only possible configuration, I must have red move to the right and blue will have to move up. Now red and blue meet again here. So what happens now? Now blue will come from the left and red from the bottom. Blue is less than red. So if I have blue from the left and red from the bottom, this is the only possible configuration. So now blue will have to keep going up. And red will have to keep going right. So this, and then similarly, I can color these two paths. So basically, this gives me a unique way to go from the bumpless pipe dream to the to a state of my lattice model. And the general idea is the first time so I start coloring paths, and the first time two pipes meet, the larger color goes through, and then whenever they meet again, the larger color never goes through. It always goes right, like here. So this is, even in general, this is not hard to see that this will give you a bijection between the two parts. Okay, so we have this bijection, and we know that the lattice, we know that the partition function is a sum of weight of state over states. So we know states are in partition with bumpless pipe dream with key W. So now what we have to do is we have to compare the weight of the bumpless pipe dream and the weight of the state. And to do this, basically, notice that here we take this product over empty tiles, and empty tiles like this one will correspond to this type of configuration at a vertex. So for example, this one. And this weight is the same as this weight. And then similarly for tiles like this, they will correspond to configurations of this form, and the weight is the same. So now we trivially get back the theorem. Any questions? So I do want to emphasize that the initial proof is pretty hard, and that this becomes very easy only when you go to the lattice model. Like so like I couldn't explain this fast, the initial proof. Okay. So now let me briefly mention the second model. So this is the model called the P model in BFHTW. They will have different weights to ours. They look similar, but they're somewhat different. They will also have different conventions. So their paths will start on the left and they will end on the top. And they also have a similar theorem which says that the partition function is equal to the Grothendieck polynomial. The proof is, I believe, similar modulo something they do. I think they can comment on what the proof is, but my understanding is that they use a D model, and they show that the D model is equal to this via standard techniques, including integrability, and then they show that the P model is equal to the D model. I'm not entirely sure if the P model is integrable, so maybe that's a question. Is the P model?
Yeah, I think they're all integrable. It's just a question of like sort of which way you simplify the pipe dreams, and so anyway.
Okay. Yeah. Anyway, okay. So there's this model, and now we can introduce other combinatorial objects, which are called pipe dreams, and they will be the same style of tillings of n by n grids, but now we only use the following squares. We use the empty square and these two squares. So for example, this is one example of a pipe dream. And then there's a theorem that says that the Gautendick polynomial is the sum over these pipe dreams with a certain key, W. And then we have certain weights. And the weights will only be determined by these tiles. So this theorem was, or maybe I should say certain versions of this theorem were known before. And what happened is one may use the lattice model to give, again, a relatively easy proof of this theorem. Now, there isn't a immediate proof as ours, because you have to do the following thing. So for a pipe dream P, you may define something that's called its reduction. That's also a pipe dream. They will have the same key. So then what you can match is you can match states in the models with sets of P such that P has the same reduction. So by doing this, basically you can prove the theorem. And it's interesting that the states in their model account for the existence of possibly many pipe dreams P with with the same reduction. Okay, so this is briefly what's happening there. And there's a fact, there is no weight preserving bijection between bumpless pipe dreams and pipe dreams. So what this essentially means is that you cannot go from the sum over pipe dreams to the sum over bumpless pipe dreams by matching terms together. So this, I think this is a different way of saying that our two models are different.
Valentin, I have a small question.
Yeah.
Is it the same as duality, like statement B when you take gamma or delta i's, or it's essentially different from just the way how you embed smaller groups?
I don't know any proof that these two are equal in the same spirit of statement B. To prove that they're equal, essentially, I think you have to prove that they're both the Grothendieck polynomial, or that they satisfy the same functional equations.
So there is no some sort of Gray-Yan-Baxter equation for between.
Not that I know. No.
Okay.
No. At this point, no.
Thank you.
But that would be an interesting thing to explore.
Yeah, of course. Okay, so I'm running out of time, so let's see what we can do here. Okay, so what I've talked about so far has been two applications of our lattice model that are very easy to see and to explain. But in fact, there are many applications, and most of these applications will just be reproofs. So one such application is proving a Cauchy identity for these Grothendieck polynomials. Another application would be to prove this somewhat interesting identity. So you can flip the alphabets x and y, and then you get back the same Grothendieck polynomial, but with w inverted. And this can be seen easily in our model. What you have to do is basically you have to flip across the diagonal to see this. So once you flip, if you recall, to go back. Well, so the x, if you flip across this diagonal, the x's and the y's get replaced one by the other. Okay, some other applications. You can specialize. So what we do, what Travis and I do, is we specialize to W of vexillary permutation. So this means it avoids the pattern 2, 1, 4, 3. And in particular, what this implies for our model is that there won't be any vertices. So any configurations that look like this for the vertices. And then we may build a semi-dual model for flagged double Grothendieck polynomials. And this is useful because, so by building this semi-dual model, okay, and then finally, we may also study factorial Grothendieck polynomials, which are the stable limit of these polynomials. So what is, so I'll try to be very brief and finish not too late. So what is the idea with the semi-dual model? What we can do is, because we don't have this configuration, this vertex configuration, we may uncolor our model. And then what we do is basically on the diagonal, we flip, we replace uncolor by color and color by uncolor. So basically we will have this, so the left will be the weights in the initial model, and the right will be the weights in what we call the semi-dual model. So what we do is basically here we have no color, so we get color, color. Here we have color, color, so we get no color, and so on and so forth. And then we get a different model, but there will be a correspondence between the two. So we'll have this model. So for example, this is a state in the first model, and this will be the corresponding state in the dual model. So for W vexillary, we may associate a partition and a flagging to it. And then the semi-dual model is integrable, and it will represent this this Grothendieck polynomial G lambda W F W. And this is in fact the same as G W beta. So now why is it useful to introduce this semi-dual model? And the reason is the semi-dual states will be easier to see that they are in bijection with marked GT patterns, which is a special version of GT patterns, which where you mark certain entries, and these will be in correspondence with set-valued tableau. And then by this correspondences, we may reprove a theorem of Book, which says that these polynomials are a sum over set-valued tableau, over certain set-valued tableau. And then there's other theorems, and many of them are in this spirit. Basically, once you have the lattice model, it is very easy to look at the states and somehow characterize the states combinatorially. And this gives you this, this theorem immediately, that your partition function will be a sum over these states for which you understand the combinatorics and also the weights quite well. Okay, so finally, in the last, let's say 5 minutes or so, I want to briefly mention structure coefficients. So what are structure coefficients? Let's look in the simplest case for the Schur polynomial. We can think of the Schur polynomial as the character of the irreducible v lambda of the representation of G ln C, which is semi-simple. So because of semi-simplicity, this tensor product of v lambda tensor v mu will break down as a direct sum of irreducibles. And of course, each irreducible will appear a certain number of times in this direct sum. So these coefficient will be what I call structure coefficient. And because of the representation theoretic interpretation, one can immediately say that these will be non-negative integers. And it is a somewhat important problem to compute these coefficients. And by compute, I don't mean basically get them from the representation theory, but rather, given these three partitions, give a very simple combinatorial formula that spits back this coefficient. So this equality is equivalent to saying that we may multiply Schur polynomials and expand the result in terms of Schur polynomials, and we'll get back the same coefficients. Okay, so the problem is give a combinatorial algorithm for computing these coefficients. These are called the Littlewood-Richardson coefficients because Littlewood and Richardson gave the first such combinatorial argument in terms. These would be computed in terms. This would be the numbers of certain tableau of a certain shape and a certain weight. Their proof was not correct. In fact, I think they only proved it in certain special cases. There were, I think, a few other proofs that were incorrect. And then at some point, there was a correct proof due to Schutzenberger and also, I think, independently by Thomas. And then many people are interested in things like this, and many other formulas surface. So there are many combinatorial formulas for these Littlewood-Richardson coefficients in terms of Yamanouchi words, in terms of the Remo-Whitney rule, Knudsen-Tao Woodward puzzles, and so on and so forth. And what I want to focus on is this Knudsen-Tao Woodward puzzles. So it was a big breakthrough of Xinjustin, where he reinterpreted these puzzles from the point of view of integrable systems. The integrable systems will be slightly different in the sense that they will be triangular. But essentially, they will work in the same way. For each, you will have certain boundary conditions that depend on these partitions. And then you will set the boundary conditions, and then the interior you can allow any configuration from a given set of configurations. And then you can also compute a partition function, and essentially this will be the partition function of such a system. So what happens is you may give you may say we computed these. You may compute these as the partition function of such a system by giving a completely integrable systems proof. So what I mean is there are lattice models for these objects, and there is a lattice model for this object. So proving something like this becomes an exercise in using the Yang-Baxter equation and similar techniques. So this was a big breakthrough. And then Wheeler and Xinjustin then gave formulas for the structure constants for the Grassmannian Grothendieck. This is in a recent paper in Krell. And this is again in terms of these puzzles or triangular integrable systems. But as far as I know, the structure coefficients for the general Grothendieck, beta Grothendieck polynomials, this is a still open and somewhat important problem.
What about for Schubert polynomials? It's still open for Schubert, no?
Yeah.
That's kind of really important question.
Yeah. So I mean, I think one of the reasons this is important is because you can recover the Schubert case from here. So it's yeah. But there are, I think there might be people working on it. So I think at some point, Michael Wheeler had some better understanding of these coefficients in certain cases. So I'm not sure. This is an active area of research, I think is what I'm saying. So now this is the last slide, and I'll end in a minute or two. So structure coefficients are very important, and you may study them for functions in functions like Schubert polynomials or Grothendieck polynomials. But these structure coefficients may appear in other contexts. And one such context that I know of from Anna is the following. So this is an observation, and I want to end with this because I haven't said anything about p-adic stuff, and I want to say something about p-adic stuff. So so these objects were introduced some time ago. So if you consider the spherical Whittaker function for GLN over QP, and you also consider the spherical Whittaker function, but now the double 2 cover, so the metaplectic 2 cover of GLN, again over QP. There was this observation by Chinta and Pushkash, maybe also by Ganos, that you may write a product of these 2 functions, and then you may expand this product in terms of these 2 metaplectic Whittaker functions. So this is a typo. And then you'll have similar coefficients, and these coefficients have very nice properties in the sense that there will be only integers appearing, and I think they might also understand the sign. I'm not sure if the sign is always positive, but I think they might understand the sign as well. But this is a bit imprecise, so I'm not saying too much. Maybe you should ask Anna or Gautam about this. So now a question becomes, can you write down formulas to compute these coefficients? And what is the representation theoretic meaning of these coefficients? And I think there's no answer for either of these questions. But if you might want formulas for these coefficients, one way to attack this problem is possibly via these lattice models for W lambda and W mu, which have been, we've talked about these previously. Yeah, so this is it for today. Thank you for having me. And let me know if you have questions.
Thank you, Valentin. Stop recording.